today's video I'm going to be talking to you about Green's theorem. And in this video I'm not going to be proving the theorem, I'm going to be stating it and working a couple of examples. I expect I'll come back in the next video and I will prove the theorem itself, or at least kind of like the first statement of it. And also maybe this other formula that we're going to get from Green's theorem. Okay, so I think I'm just going to start off right now by just kind of stating the theorem, what it is, what we're going to use it for, and then I'll work a couple of examples. So there's going to be a lot of kind of fine print to go along with this, and you know, now that I think about it, I think I might just pause, write it up there, and then resume recording. So I'll do that. All right. So what we're saying is that if we've got a path integral over a closed curve C that's oriented counterclockwise, that of something that is like what we get back when we're integrating a vector field, that we can actually compute this as a double integral. Okay, so this is making a connection between the behavior of an integral over a curve to the behavior of some kind of other integral over the interior of the region, which, as you might think this is surprising, and I think that this was when they discovered it, and it's very useful to as just another tool to calculate difficult path integrals, and then we'll eventually be able to use this to come up with a new area formula for just the area of a plane region. We can compute it by doing a path integral. So I think what I'm going to do is I'm just going to kind of show you how it works. Normally I would give you a theorem, I would prove it, but I don't think that that's going to be the most important thing for you to learn today. I think the most important thing for you to learn is how to actually compute these Green's theorem integrals, right? Integrals that you need to use Green's theorem to compute. All right, so I'm going to just pause and set up for an example. All right, so first example, suppose I'm confronted with a path integral, and it's this kind of closed path here, and I've got it. What I'll tell you is if you actually tried to parameterize these curves and run it through, it'd be kind of cumbersome. It wouldn't be super easy, and it is easier to apply Green's theorem. So what I'm going to do is I'm going to notice, okay, this C is closed. If I am using kind of that orientation, then that counterclockwise orientation I need to apply Green's theorem. And I'm going to say, all right, if I call this the interior region R, then this is going to be equal to the double integral over R of nx minus my. Okay. And, well, we'll just need to figure out what nx and my are. Okay, m is y to the 3, so my is equal to 3y squared. And nx is going to be 3x squared plus 3y squared. Okay. Notice also, because nx and my are not the same, this vector field is not conservative, and therefore I'm not going to get 0 when I rotate or when I integrate all around a closed path. But if it was conservative and I was going to get 0 when I integrated all the way around a closed path, I could see that in my double integral, because nx would be equal to my, and I'd be integrating 0 dA, and I would get 0 back. Okay, so I just thought I'd point that out. All right, so really what this is a double integral, and I think I'm going to want to go with respect to y first, as y runs from x to the 3 up to x. And then dx, x is going to run from 0 to 1. Okay. And then my integrand is going to be nx minus my. So 3x squared plus 3y squared minus 3y squared is going to be 3x squared. All right? And you might be like, oh, this feels off. But remember, this is just a constant with respect to y. And so I'm going to have the integral from 0 to 1 of 3x squared y as y runs from x to the 3rd up to x. And we're going to integrate that with respect to x. And now this is equal to, I'll give myself a little more room in case I don't know if I'm going to run out, but I wouldn't want to run off the shot. So I'll have 3x squared x is 3x to the 3rd minus 3x squared x to the 3 is going to be 3x to the 5. Okay, and then this is going to be not too hard to compute from here. I think I'm going to say that this is 3/4 x to the 4th minus 3/6 x to the 6. As x runs from 0 to 1, so it'll be 3/4 minus a half minus 0 is going to be 1/4. Okay, now it's actually much easier than running the path integral over those two paths. All right, I think I'll pause for a second and bring up something new. All right, so I think the next thing I want to show you is formulas that we can use that would give us the area of a region. Okay, so just to recap, what we already know is that, the area of R is equal to the double integral over R of dA, or 1 dA. That was something we learned, quite a ways ago in this course. But what I'm telling you is that equivalent to this, and this is another theorem that I expect I will prove in the next video, I haven't really planned that far yet, is that this area is going to be equal to the path integral over that closed curve C that's oriented counterclockwise of x dy. So it's going to be the path integral over C, where C is again the same boundary of region R, where R is simply connected and C is meeting the conditions. Hold on, let me just tell you exactly which conditions those are. That would be if C is a simple closed piecewise smooth curve, okay, and R is a simply connected plane region. And I think some of those terms you might not know what it means, but again, like I said in the last video, this is not a topology video, or this is not a topology course, so we're not going to really go into connectedness and all of that stuff. We really don't need to worry about it. What you need to not have happen is that it's not like, a completely disjointed two regions. You want a region with a curve that serves as a boundary. All right, so this is going to be the path integral of x dy. This is also equal to the path integral over C of y dx. And then there's a third formula where you kind of combine those two together. And let me see where it is. I think it's half of x dy minus y dx. Pardon me, it's the negative of this. And I mean, it could be positive when you orient it the other way, but I'm going to say it's the negative of that. And that's equal to, half the integral over C of x dy minus y dx, right? Because if I added these two things together, I'd have twice the area. So if I added them together and then divided by 2, I would have the area. Okay. And I think that depending on the situation, maybe one of these formulas would be more useful than the other. And now I think I might go over here and just do an example of me computing an area. I think I might do an ellipse area. Let's see. That doesn't look like the best thing ever. Oh, actually, yeah, it does. I like this. All right, so the one I want to do is I want to find the area of kind of a generalized ellipse. So I want to find the area. And the region I'm particularly interested in, I want it to go A units in the x direction and B units in the y direction. Okay, it'll do. So I'm going to say that this is A, this is negative A, this is B, and this is negative B. All right, so we want to find the area of this region in here. All right, so what we're going to need to do is we've got this region, we've got the boundary, we need to parameterize the boundary. Okay, and let's see. They're doing half of x dy minus y dx, and I can kind of see that it works out real nice in the end. I'm not sure why they wouldn't just choose just integrating x dy, but maybe there's something I haven't considered. Maybe that would require me to integrate like cosine squared t, which is something I don't necessarily expect y'all to know how to do off the top of your head. So what I'm going to do is I'm going to use this shiny new formula, and this is going to be half of the integral over c of x dy minus y dx. All right, and so I need a parameterization at this point. So I'm going to parameterize this curve c with, all right, so c is, okay, r of t is going to be, if we're going a units in the x direction, it's going to be a cosine t and b sine t. I can't remember if parameterizing an ellipse that's centered at the origin is something that we've discussed this year. I sure hope that it's something that we've discussed because it's something that might be kind of useful to you. What else am I going to, okay, I'm going to also need to say that t is going to need to run from 0 to 2 pi. Okay. So r of t is that, t is stuck between 0 and 2 pi. So now I think I've got pretty much what I need, right? I've got x is a cosine t, dy is going to be y prime of t dt, and I think we can just, kind of do all that in one go. So this is equal to half of the integral over c of x is a cosine t dy is going to be b cosine t dt. So hold on. I'm not going to have enough room to write this if I write it all like that, I think. Yeah. So I'm going to have to write this. I know it's going to be a cosine t times b cosine t dt. So that's ab cosine squared t. And I know the other one's going to have a dt, so I'm going to just wait till the end for that. That's not good. All right, so it's going to be ab cosine squared t minus, okay, y is b sine t, dx is going to be negative a sine t dt, so it'll be plus ab sine squared t dt. And then you might be like, ooh, this could be getting good here because what I'm going to do is I'm going to factor out the AB. So I'll have AB divided by 2, and I think I'll just go down here. So A times B divided by 2 times the path integral. Wait, hold on. What happened? Oh, okay, I switched this to T, but I'm still looking at this as a path integral. If I switched it to t, I already know what the range of t values is. This is going to become 0 to 2 pi. And then this one also, let me integral from 0 to 2 pi. All right, of cosine squared t plus sine squared t, everyone knows that's 1. So if I'm just going to be integrating dt from 0 to 2 pi, that's just going to be 2 pi. So equals 2 pi divided by 2 times AB. This is going to be AB pi. Is that even what I'm... Okay. Evidently, that's the formula that we're looking for. Okay. So that's the way we can use Green's theorem to develop an area formula to kind of a little easier compute the area of an ellipse. Okay. And I think that, that's going to be enough for this video. I've done one where we compute a path integral by, switching over to the double integral using Green's theorem, and then I use that little extra result about the other way to calculate area. I think past here, I trust you to work the other practice problems on your own and see the different ways that you can use this. And then we'll generalize this to higher dimensions with Stokes' theorem, and we'll do some other types of integration to wrap up this part of the course. All right, well, that's it. Thank you.